All right, welcome everyone. Today, we're going to tackle a really big question, one that's at the heart of modern networking. How exactly does a data packet make its way through a Cisco ACI fabric? We're going to follow that packet step by step, and I promise we'll make it all crystal clear.
So, yeah, that's the big question, right? How on earth does a single packet navigate the complex world of an ACI fabric? I know, it can seem kind of daunting at first, but trust me, once you get the logic behind it, you've basically got the keys to the kingdom. It makes designing and, more importantly, troubleshooting ACI so much easier. Okay, so here's the plan. We'll start with the fundamentals, then we'll jump into 4 different scenarios, starting easy and building up. And at the end, we'll wrap up with the key takeaways. Sound good? Let's get into it. All right, Section 1, the fundamentals. Before we can even start to trace a packet, we've got to make sure we're all speaking the same language, you know? So let's quickly cover the 3 main building blocks of ACI that really make all this magic happen.
First up, we've got the endpoint group, or EPG. This thing is, well, it's absolutely central to ACI security. The best way to think about it is like a bucket, a logical container. You throw your servers, your VMs, whatever endpoints you have into this bucket. And everything inside that same EPG, it gets the exact same security policy applied to it. Simple as that.
Next is the bridge domain, or BD. Now, if you've been in networking for a while, this one's going to feel super familiar. A bridge domain is basically just ACI's fancy term for a broadcast domain. Think of it just like a traditional VLAN. It's the boundary for all your Layer 2 traffic.
And last but not least, the secret sauce that makes this whole thing work, VXLAN. This is the overlay protocol, the real magic here. It takes our plain old Layer 2 Ethernet frames, wraps them up in a brand new packet, and shoots them across the underlying Layer 3 network, between the leaf and spine switches. VXLAN is what turns a bunch of switches into a real cohesive fabric.
Okay, fundamentals are down, so let's jump right into our first scenario. We're going to start with the easiest one possible. We've got 2 endpoints, they're in the same EPG, they're in the same bridge domain, and they're even using the same VLAN. Couldn't be simpler. So first, let's picture 2 hosts, H1 and H2. They're plugged into the exact same ACI leaf switch. Yeah, it really doesn't get more basic than this. So what happens when H1 wants to talk to H2? Well, the leaf switch gets that packet, does a quick lookup in its local table, and goes, oh, I know where H2 is. It's right over there on port 1/2. And boom, it sends the frame right over. The traffic never even leaves the switch. It's just simple, old-school, local switching, exactly like you'd see on any regular switch. So, to sum it up, H1 sends the frame. The leaf does a quick Layer 2 lookup. It finds H2 on another local port, and it forwards the frame. That's it. All done right there on the one switch. Okay, piece of cake, right? But what if the endpoint we want to talk to, let's call it H3, isn't on the same switch? What if it's all the way on the other side of the data center, plugged into a totally different leaf? Well, now things get interesting. Now the fabric has to wake up and do its thing. Okay, so H1 sends its packet. The first leaf switch, our source leaf, gets it and realizes, hey, H3 isn't one of my local guys. And this is where that VXLAN magic kicks in. The leaf takes that original frame, encapsulates it, and slaps a VXLAN header on it. And the most important part of that header is this thing called the bridge domain VNID, or BD_VNID. For this bridge domain, it's that big number, 159.90752. Think of that number as a tag that tells every other switch in the fabric exactly which Layer 2 network this packet belongs to. So this newly wrapped VXLAN packet travels up to a spine switch and then down to the destination leaf. And when that leaf sees the packet, it looks at that BD_VNID and immediately knows, aha, I know this network. This belongs to our bridge domain. It then just unwraps it, stripping off the VXLAN header, and you're left with the original Ethernet frame. Then it just forwards it out the right port to H3. Super efficient.
So let's just run through that one more time. Source leaf wraps it up with the BD_VNID. The packet zips across the fabric. The destination leaf unwraps it and sends it on its way. That BD_VNID is the key. It's like a universal translator that lets all the switches communicate about this one Layer 2 network, no matter where they are physically. Okay, on to scenario 2. We're going to build on what we just learned. What happens if our endpoints are still in the same logical group, the same bridge domain, but on their local switchboards, they're actually using different VLANs? This is actually a super powerful feature in ACI. It's sometimes called a Layer 2 gateway. What it means is ACI can bridge traffic between 2 different VLANs without needing a router at all.
The MAC addresses don't change, nothing gets routed, all it does is translate the VLAN tag. And let me tell you, this is a lifesaver when you're trying to merge different departments or old legacy gear into your shiny new ACI fabric. So let's go back to our local switching example. H1 sends a frame, and it's tagged with its local VLAN, 2014. The switch gets it. It knows that H1 and H2 are in the same bridge domain, but its configuration also says that H2 is expecting traffic on a different VLAN, 2025. So what does it do? It just handles it. It gets the frame on 2014, does its lookup, and before it sends it out to H2, it just swaps the tag to 2025. It's completely seamless. And check this out, this is the beautiful part. Across the fabric, almost nothing changes. The source leaf still encapsulates the packet with that exact same BD_VNID. The packet still crosses the fabric in the same way. The only, and I mean only, difference is what happens right at the end. The destination leaf knows that H3 needs VLAN 2025, so it makes sure to tag the frame with 2025 before sending it out. The core of the fabric doesn't even know or care about the local VLANs. So the big takeaway here is that the fabric itself doesn't care about your local access VLANs. The forwarding inside the fabric, using that BD_VNID, is exactly the same. All that VLAN translation magic, that happens at the edges, on the leaf switches. It's the destination leaf's job to know the right VLAN for its connected endpoint and tag the packet correctly on its way out.
All right, let's mix it up again. Let's add security into this equation. What if our endpoints are in the same bridge domain, so they're on the same L2 network, but we've put them into different security groups, different EPGs? What happens then?
This is a really important point. The actual forwarding, how the packet gets from A to B, is exactly the same as what we just saw. Nothing changes there. But because they're in different EPGs, they're in different security zones, so by default they can't talk. To allow them to communicate, we now need to put a contract in place between them. So take a look here. H1 is in EPG 1. H3 is in EPG 2. The packet's journey is going to be identical. It's still going to get bridged using that BD_VNID. But here's the crucial part. If you don't have a contract defined that says EPG 1 is allowed to talk to EPG 2, that leaf switch is going to see the packet and just drop it. End of story.
This really gets to the heart of ACI's philosophy. You have to separate two questions in your mind. One, how does a packet get somewhere? And two, is a packet allowed to get there? The how is all about forwarding lookups and hardware. The is it allowed part? That's all about policy. And that's what contracts are for. Forwarding is a lookup. Permission is a contract.
Okay, so let's just pause and look at where we've been and where we're going. Everything up to now, it's been layer 2 switching, all within the same bridge domain. Our next scenario is a whole different ballgame. We're moving to layer 3 routing between different bridge domains. It's a big shift from bridging to what's called VXLAN routing.
All right, here we go. Scenario 4, the final boss. We've got endpoints in different EPGs and in different bridge domains. This means they're in completely different IP subnets. So there's no way around it. We absolutely have to route between them.
Let's start locally one more time. H1 is in BD1, H2 is in BD2, but they're on the same leaf switch. Well, in this case, the leaf just acts as a router. It's the default gateway for both of them. It does a normal routing lookup, changes the MAC addresses, you know the drill. It's just like standard inter-VLAN routing that's been around for decades, all happening inside one box.
But you know what's coming next, right? As soon as we move that destination, H3, over to a different leaf, the game changes completely. Now the fabric itself has to do the routing, and this is what we call VXLAN routing.
Okay, now pay close attention here, because this is the big reveal. Look at the identifier being used to encapsulate the packet now. It's not the BD_VNID anymore, is it? Nope, because we're routing, the fabric uses the VRF_VNID. That VRF identifier basically tells the destination leaf two things. One, hey, this is a routed packet, not a bridged one. And two, here's the specific routing table, or VRF, that you need to use for the final lookup. So let's walk through it. H1 sends a packet to its default gateway, which is the source leaf. That leaf does a routing lookup and encapsulates the packet using the VRF/VNID. It zips across the fabric to the destination leaf. That leaf uses the VRF context to finish the routing decision, and then it sends a frame out to H3, properly tagged with its local VLAN. It's a beautiful, distributed routing process.
Phew, okay. We have covered a ton of ground, right? We've followed that little packet from a simple local switch hop all the way to a distributed route across the entire fabric. So let's just take a second and nail down the key takeaways.
Okay, here's the cheat sheet. When traffic is in the same bridge domain, it gets bridged, and the fabric uses the BD_VNID to do it. If you've just got different local VLANs, no problem, the leaf switch handles the translation. If endpoints are in different EPGs, remember, the forwarding is the same, but you need a contract to allow it. And finally, if they're in different bridge domains, it's got to be routed, and the fabric uses the VRF_VNID for that.
And really, that's what it all boils down to. When you're troubleshooting, the first question you need to ask is, should this traffic be bridged or should it be routed? Because if you can answer that, you know exactly what to look for in the fabric. You're either hunting for a BD_VNID for bridging or a VRF_VNID for routing. And that, right there, is the key to solving most ACI connectivity problems. So I'll just leave you with this to think about. Now that you can follow the packet, how is that going to change the way you design, and more importantly, the way you troubleshoot your ACI fabric? Thanks so much for joining.